Hello, Honors Geometry. We are today working on lesson 11.1, which is writing quadratic functions. So we are going to write quadratic functions that are given 3 points. And so our two learning targets are, number 1, to explain why 3 points are needed to determine a parabola. And number 2, we want to be able to determine the quadratic function that passes through 3 given points on a plane. So recall, if you're given any 2 points on a coordinate plane, you can write the equation of the unique line that passes through those points. Those 2 points are said to determine the line because there is only one line that can be drawn through them. Given any 2 points that lie on the coordinate plane, can an equation of a unique parabola passing through those points be determined? So let's practice what we learned in activity 10. We're going to write an equation of a parabola that goes through the 2 points 2, 0, and 5, 0. So those are actually the x-intercepts. And so we learned how to take those x-intercepts and put them into factors and then multiply them out to get an equation. And so that's what we're going to do here. So let's take this x minus 2 times x minus 5. And if we FOIL that out, we will get a function, a parabola, f of x equals x squared minus 5x minus 2x, which is minus 7x, and then plus 10. Now it says, replace 0 in your equation with a y to write the corresponding quadratic function. Well, I didn't write mine with a 0. I went right to f of x, but I'm going to replace it with a y. Y equals x squared minus 7x plus 10. Okay, so that's a parabola. And we could use substitution to check to see that those points do lie on that graph by plugging in a 2 for x and noticing that we're going to get out a 0 for y. So if y equals 2 squared minus 7 times 2 plus 10, we're going to get 4 minus 14, which is negative 10 plus 10. That is 0. And the same is true for 5, 0. If we plug in 5, you get 5 squared minus 7 times 5 plus 10. Again, you get 0. 25 minus 35 is negative 10 plus 10 is 0. So those 2 points do lie on our line, so we know that's a good line for those points. So now it's going to ask you to graph your quadratic function from item 1 on a graphing calculator and to also graph 2 other functions on the calculator. So I'm going to switch over to my graphing calculator. If you have yours, you can do the same and we will be able to take a look at the graphs. So let's go back to our y equals here and clear that out. So I'm going to plug in the equation that we just wrote, which is x squared. Then it's minus 7x, and finally plus 10. Okay, and then they want us to put on the same screen. Okay, so let's just graph that one first. So I'm going to do a regular window. My window looks like it's standard, so I could just hit graph. And so there's my graph, and you can see the intercepts are there at 2 and 5. So what we want to do now is graph 2 other functions they gave us. They gave us under y2, we're going to put 2x squared and then minus 14x and plus 20. Okay. And then under y3, we'd like to put negative x squared plus 7x and then minus 10. So you can kind of see that these equations are related to each other. Hopefully you can see that we have a multiple of each other, times 2 or times a negative 1. Well, anyway, when we hit graph, we get this. And so you can see that all 3 of these parabolas actually have those same intercepts, but they are not the same parabola. There's 3 unique parabolas there. Okay, so that is a problem. So with lines, 2 points will determine exactly one line. Okay, but that's not true for our parabolas. So we went ahead and did our graphs. Okay, now we can talk about to describe the graphs. Do all 3 parabolas pass through 2, 0 and 5, 0? Yes, they do. Okay. But we had 2 parabolas that opened up, 1 parabola opened down. They were different widths. So the parabolas were different widths. Okay, some up, some down. So can any 2 points on a coordinate plane determine exactly one parabola? No. Many parabolas could share those 2 points. So many parabolas can share those 2 intercepts, actually, those 2 x-intercepts. But they are not the same parabola. So this basically leads us to our main part of our lesson today, which is writing an equation of a parabola with 3 points. And that's where we're at now. So a unique parabola defined by a quadratic function can be determined by 3 non-collinear points. And that's what we're going to spend most of our time doing, is we're going to actually take 3 points and we are going to write a system of equations in order to solve. So we have our 3 points. We have the points 1, 2, 3, 0, and 5, 6. And what they're going to have us do in these steps is write equations in terms of A, B, and C by substituting each point into the standard form. So we're going to start with the point of 1, 2. Okay, so we're going to put, for the ordered pair 1, 2, 1 is x, 2 is y, and we're going to go ahead and plug it into the formula. So if y equals, well, we're going to put in 2 equals, and then it's a times 1 squared plus b times 1 plus c. And if we simplify it down, we get 2 equals a plus b plus c. All right, hang on to that. We're going to need that in a few minutes. For the second equation, we're going to do the same thing, only we're going to use the ordered pair 3, 0. So now 0 equals a times 3 squared plus b times 3 plus c. So 0 will equal 9a plus 3b plus c. And that's equation number 2. Hang on to it for later. And finally, we are going to have a third point, 5, 6. So 6 equals a times 5 squared plus b times 5 plus c. And that means 6 equals 25a plus 5b plus c. And now we have 3 equations with 3 variables that we'll be able to solve. And ultimately, we'll get the a, the b, and the c. And that'll be our equation. All right. Now, let's take those 3 equations and we'll put them together in a group here. So a lot of times when you see a system of equations, you'll see it written with a big brace. And so our first equation was a plus b plus c equals 2. Then we had 9a plus 3b plus c equals 0. And finally we had 25a plus 5b plus c equals 6. And that's what we want to solve. So you should have learned how to solve a system last year, but I'll take it kind of slow just so you can remember how to do it. When you have 3 equations and 3 variables, you really have to work with 2 equations at a time in order to make this happen. So we are going to try to solve, and it's going to take up a little space, so I'll probably have to use the side, but let's go ahead and just do a little elimination. Since we have 3 variables, we can't work with 3, so we're going to have to eliminate 1. So what I would like to do is eliminate the c, and I can eliminate the c by taking the first equation, multiplying it by a negative, and then adding it to the second equation. So if I take the first 2 equations, so a plus b plus c equals 2, and 9a plus 3b plus c equals 0. If I change this one to multiplying by a negative, so now I have negative a minus b minus c equals negative 2. And if I keep the second equation, 9a plus 3b plus c equals 0, now I can add these 2 equations together to get 8a plus 2b equals negative 2. So now I have an equation that only has a's and b's in it. Okay, well, I also need to do that with maybe equation 1 and equation 3, if I work with those two. So again, now I'm going to move this off to the side. Let's maybe work with equation 1, which I know is negative a minus b minus c equals negative 2. And I put it with equation 3, which is 25a plus 5b plus c equals 6. When I add, then I'll get 24a plus 4b, c's will cancel, equals 4. So now I have two equations that have a and b in them, and I can put them together. Okay, so I have 8a plus 2b equals negative 2. And I have 24a plus 4b equals 4. So as it is, nothing cancels, but I could change maybe the top equation, and maybe if I multiply the top equation by negative 4, maybe I can make it happen. So that's negative 32a. I don't want to do negative 4. I think I want to do negative 2 to make a negative 4. So let's change that. So that'll be negative 16a minus 4b equals 4. And then I'll have 24a plus 4b equals 4. Now the b's cancel, and I get 8a equals 8. So a equals 1. So I have the a. All I have to do now is back substitute to get the others. So if I go back into equation, so if I take a as 1, so if I use the 8a plus 2b equals negative 2, but I let a be 1, 8 times 1 plus 2b equals negative 2. 8 plus 2b equals negative 2 minus 8. 2b equals negative 10. So b equals negative 5. Okay, so now I have the a and the b. And the last thing we would do is plug them back in to get the c. And so if you plug a and b back in, maybe to the first equation, then you'll have, so we have our a is 1. We know that our b is negative 5. 1 plus negative 5 plus c equals 2. So negative 4 plus c equals 2. So c equals 6. So our equation will be y equals, since a is 1, it's going to be 1x squared. B is negative 5, so minus 5x. And c is 6, and that's our equation. So it's a bit of work, but if you're careful with your steps, you can get an equation. You can get your a, b, and c. We could graph it to see if those points are actually on that line. So if we use what we've learned in previous lessons about finding a vertex of that graph, so if I do negative b divided by 2a, that's negative times negative 5, divided by 2a, 2 times 1, so that's 5 over 2, or 2.5. Okay. And then if I plug that back in, then I'm going to get, if I do y equals 2.5 squared minus 5 times 2.5 plus 6, then we actually get negative 0.25. And so that's over here. So we get an ordered pair of 2.5, negative a quarter, which is right about there. And then if we pick other values to plug into our function, like if I plug in a 0, I know I get out 6. And if I plug in, a 6, then I know that I will also get out a 6. So you will see that when you draw the graph, you will see those points actually are very close to there. I see a point at 1, 2, that's right there. See a point at 3, 0, that's right there. And 5, 6. If I drew my graph right, I would see a point at 5, 6 as well. So let's drop back in a little bit nicer. And there we go. 5, 6. Okay, it's just a way to look at your points on there. All right, so for the the practice problems, there's a lot to practice, and these do take a while. So we're going to do some of those in class, and then hopefully you will get the process down. And then tomorrow we will also look at how to put these into the computer or your graphing